Yes, students, all of you, good morning. Welcome to the session. Is it screen is visible?
Yes, sir.
Yes, thank you. This is a continuation of network theory concepts. I started coupled circuits in the previous class. Continuation of that. With respect to coupled circuits, that is a magnetic circuits. I given these fundamentals. All these I already discussed in the previous session. It's minimum fundamentals that I already explained. Students, this is the definition of the flux I given, MMF by reluctance. Then by neglecting the saturation, always the flux is directly proportional to the current. All these fundamentals in the previous session that I explained, students. Then here I am giving the some note points. Please concentrate. Self-inductance is with reference to the same coil. We know that how to define the self-inductance and mutual inductance. Self-inductance is with reference to the same coil and its own turns and its own current and flux. But however, the mutual inductance is between a set of coils. If you want to define the mutual inductance, minimum is how many coils? Minimum two coils. But more than that, also we can define the mutual inductance. But there must be minimum two coils. Then only we can define the mutual inductance. And the two coils must be mutually coupled. That is magnetically coupled. Magnetically coupled, then we can define the mutual inductance. When two coils are in a close proximity to each other, the magnetic flux caused by current in one coil links with the other coil, thereby inducing voltage in the later. This phenomena is known as mutual inductance. We know that if the two coils are coupled to each other, let these are the two coils are coupled to each other, magnetically coupled to each other. Then later we are giving the current to only one coil. So we are giving the supply to only one coil, and this coil carrying the current. This coil is carrying the current. Then whatever the flux produced by this coil is links with the other coil. Then there is a induced EMF in the other coil. That induced EMF is nothing but a mutual induced EMF. Then between these we can define the which one mutual inductance we can define. This is the case. When two coils are close proximity to each other, the magnetic flux caused by current in one coil. That means this coil is carrying the current, then it produces the flux. This flux links with the other coil. Then there is a induced EMF in this coil also. Then this principle is nothing but a mutual induction principle. Then because of that, there is a mutually induced EMF. Then we can define the mutual inductance. That means what are the points you remember here, friends? Self-inductance is with respect to one coil only. But mutual inductance is with respect to minimum two coils. Minimum two coils. More than that also we can define. Now see small formulas here that you know already. Minimum fundamental. Here concept of self-inductance. Concept of self-inductance. Concept of self-inductance. Yes, friends. Let's consider this is the coil. A coil is this iron core. On this iron core, we are placing the coil. Self-inductance is with respect to one coil only. Okay. For this coil, we are giving the supply. Let this V equal to Vm sin omega t. Let this is the current I. Let this coil is carrying the current. This is the direction of the current. Okay. Now, how to find the, if any, I told already, if any conductor carries the current, around the conductor, magnetic flux is produced. Yes, the direction of the magnetic flux is produced. Then our magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are nothing but a flux lines. Yes, friends. This is the one solenoid coil. If this carries the current, there is a flux. How to determine the direction of that flux? The flux direction is determined by using right hand thumb rule. Then if you apply the right hand thumb rule, then how to determine the direction of the flux, friends? If you apply the right hand thumb rule, yes, then this is the, I told already this concept. This right hand thumb rule you can apply in two ways. If it is a straight conductor, thumb indicate the current direction, curled fingers indicate the flux direction. But it is a solenoid coil or circular coil, it is a solenoid or circular coil, then curved fingers indicate the current direction, thumb indicate the flux direction. Now, what is the direction of the flux, friends? This is the direction of the flux. This is the direction of the flux. The curved fingers indicate the direction of the flux. Yes. Yes. Is it okay, students? Then this is the direction of the flux. Apply the right hand thumb rule. Okay. Now this is the flux. Then according to, then if these conductors carry, whenever these conductors are carrying the flux, then there is an induced EMF. That induced EMF is nothing but a self-induced EMF. Then what is this self-induced EMF? The self-induced EMF equal to, yes, minus n into d pi by dt. Minus n into d pi by dt. This magnitude is given by Faraday's second law. Direction is given by Lenz's law. This is the magnitude. This term is the magnitude. Magnitude according to which law, friends? According to Faraday's second law. Actually, this induced EMF is the statically induced EMF. I think you know this one. Even in the starting fundamentals also I explained. This induced EMF is the static, in AC analysis that I explained. This induced EMF is the statically induced EMF because conductors are stationary, flux is time variant flux. That's why it is a statically induced EMF. The magnitude of the statically induced EMF is given by according to Faraday's second law. This direction is given by, yes, friends, according to Lenz's law. According to Lenz's law. That means 2 points mainly you remember here. There is a concept of statically induced EMF and dynamically induced EMF that I already discussed in the AC analysis. The direction of statically induced EMF is given by Lenz's law. Magnitude is given by Faraday's second law. The direction of dynamically induced EMF, like in DC generator. In DC generator, whatever the EMF is there, that is the dynamically induced EMF, because where the conductors are rotating, flux is constant. With respect to dynamically induced EMF, direction is given by Fleming's right hand rule. Magnitude is given by flux cutting rule. Magnitude is given by flux cutting law. Yes, friends. Okay, this is the self-induced EMF. What is this EMF? Self-induced EMF. You can also write this formula minus dn pi by dt. Number of turns into flux. What it gives, students? Come on. Number of turns into flux gives the flux linkage. That is equal to minus d psi by dt. Is it okay? Yeah, this is the self-induced EMF. But here I want to define the self-inductance. Then to define the self-inductance, I'm modifying the equation like this. E self equal to, yes friends, minus n into d pi by dt. Please multiply and divide with di. Multiply and divide with di. Small modification here in order to define the self-inductance. Minus n into d pi by dt. Multiply and divide with di. Then I'm writing like this. Minus, yes friends, n into dn pi by di into di by dt. This is equal to minus L into di by dt. What is L here? Where L is the self-inductance. L self, where L is the L self. Then what is this L? I am replacing this as a L. dn pi by di. dn pi by di. Okay, this is, or simply you can write n pi by I. N pi by I. Okay, this is the concept of self-inductance. The self-inductance is defined based on the self-induced EMF. Clear, students? That is, the self-inductance is, this is a change of flux due to change of current is passing through the same coil. The change of flux in a coil due to change of current is passing through the same coil. It is not another coil. Okay, this is what exactly a self-induct. Unless otherwise specified, inductance means you take the self-inductance. If it is given that mutual inductance, then only you take the mutual inductance. If unless otherwise specified, you take the inductance means self-inductance. Sir, why this negative sign, sir? It is according to Lenz's law. What Lenz's law states? Always response opposes the cause. Who is the response here? Induced EMF is the response. Who is the cause here? Change of flux. That is, according to Lenz's law, the induced EMF always opposes the rate of change of flux. Very important. Here, induced EMF is not directly opposing the flux. It is opposing the rate of change of flux. That is very important. If one quantity opposes the rate of change of another quantity, then angle between those two quantities is 90 degrees. If one quantity directly opposes the another quantity, students, for example, x equal to minus y, then what is the angle between x and y? 180 degrees. If x equal to minus dy by dt, then what is the angle between x and y, students? It is a 90 degrees. That point to remember. If one quantity directly opposes the another quantity, then angle between those two quantities is 180 degrees. If one quantity opposes the rate of change of another quantity, then angle between those two quantities is 90 degrees. That's the reason why, what is the angle between induced EMF and flux? The induced EMF and flux is never be 180 degrees. It is how much? It is a 90 degrees. Even electrical students that you know with respect to transformers also. Once you are drawing the phasor diagram of transformer, always the angle between flux and it may be self-induced EMF, it may be mutual induced EMF. The angle is how many degrees? 90 degrees, because this quantity opposing the rate of change of another quantity. Clear, friends? Okay, this is about what exactly concept of self-inductance. Self-inductance is with respect to one coil with own turns, own flux, and own current. The current is passing in the same coil. The flux is also linked with the same coil. The turns also for the same coil. Okay, that is nothing but a self-inductance concept. It is a self-inductance concept. Yes. Then here I want to define concept of self-inductance and mutual inductance concept by considering the transformer. Or it is a transformer is also one of the coupled circuit. No doubt at all. Transformer is also one of the coupled circuit. Yes, friends. Yes. Here you are understand. I think you are understood this what exactly self inductance. Now we'll see this. Just a minute. I'm adding one slide before going to this. See, before going to that slide, you understand the concept of mutual inductance. Yes. Let's consider this is the core. On the same core, we are placing the two coils, but the two coils are mutually coupled to each other. Okay, this is one coil. For this coil only we are giving the supply and it carrying the current I. Let the direction of current is like this. And one more coil is placing on the same core. But we are not giving any supply to this. Now here apply the right hand thumb rule. Then curved fingers indicate the current direction. Thumb indicate the flux direction. This is the direction of the flux. This is the direction of the flux. Now this flux links with this coil. There is induced EMF in the another coil. Let this number of turns is N1, this number of turns is N2. Whatever the induced EMF in this coil, this is the mutual induced EMF. But whatever the induced EMF in this coil, this is the self-induced. This mutual induced EMF is because of flux produced by another coil, because of current is flowing through the another coil. Understand? It is not. Whatever the flux is not its own flux. This is another coil flux. Whatever the current is not its own current. This is the another coil. That is current is flowing in the another coil. There is induced EMF in this coil. But these two coils are placed on the same core. These are mutually coupled to each other. Then how you define EM? The mutual induced EMF. EM equal to minus N2 into d pi by dt. Minus N2 into d. This flux is remains same. Minus N2 into d pi by dt. Okay, this is the mutual induced EMF. But here the concept I want to define mutual inductance. Just a small modification here, minus N2 into d pi by dt. Yes, friends. Multiply and divide with di. Multiply and divide with di. Then I'm writing like this. Minus dN2 pi by di into di by dt. Then what is the mutual induced EMF? The mutual induced EMF equal to minus m into di by dt. Yes, friends. This is the mutual induced EMF. Then what is m here? M equal to dN2 pi by di. Or simply you can write N2 pi by I. Okay, this is the mutual inductance. See the concept of self-inductance and mutual inductance, how it are defining. Now, with this knowledge, the combination of this concept of self-inductance and mutual inductance that you concentrate. Yes, friends. Let I1 is the current in coil 1. These two coils are mutually coupled to each other, while coil 2 not carries any current. We are assuming that there is a current in coil 1, but the current through the coil 2 is 0, I2 equal to 0. Then whenever the current is passing through the coil 1, then it produces the flux. Let the total flux produced by coil 1 is pi 1. The total flux produced by coil 1 is pi 1. Where pi 1 is the leakage flux. Yes, friends, you know this one. Whatever the flux produced by this coil, some flux is linked with only coil 1. Some flux is linked with only coil 1. But it is not linked with the coil 2. Understand? But total flux is pi 1. In this, some flux is linked with only coil 1. That means that flux is called leakage flux. How to define the leakage flux? That flux links with only coil 1. With respect to leakage flux of 1, I am defining. With respect to leakage flux of 2 means, coil 2 means that flux links with only coil 2. That means the flux which links either coil 1 or coil 2, but not links with the both the coils. But not links with the both the coils. Or the flux which passing through the air is called leakage flux. The flux which passing through the air is called leakage flux, or the flux which links with either coil 1 or coil 2, but not both the coils. That is nothing but a leakage flux. Then in this concept, I am assuming that pi 1 is the leakage flux. That links only with the coil 1. Where pi 2 is the common flux or mutual flux, links with both the coils. Then some flux, that is nothing but a pi 2, that links with the both the coils. That links with the both the coils. That is nothing but a mutual flux. That is nothing but a mutual flux. Yes, friends, understood. Now with this knowledge, now here I am defining self-inductance and mutual inductance. Yes. Let the N1 is the number of turns in coil 1. N2 is the number of turns in coil 2. N1 is the number of turns in coil 1. N2 is the number of turns in coil 2. Now tell the students what is the total flux? What the total primary, that is the total flux of the coil 1. In the total flux, some flux is the leakage flux and some flux is links with the both the coils. Pi 2. This pi 1, very important formulas. Pi 1 equal to pi 1 plus pi 2. Yes. Where N1 comma N2 is the number of turns in coil 1 and coil 2. Number of turns. Yes, friends. Then how much flux which links with both the coils? Then pi 2 is the common flux or mutual flux. Some factor in the total pi 1 flux, some factor only will links with the both the coils because some flux is leakage flux. That factor of flux I am defining as pi 2 equal to some factor. Its multiplying factor is k. K into pi 1. What is k here? Coupling coefficient. Where k is the coupling coefficient. Very important formula, students. Fundamental formulas with respect to gate point of view, very important. Where k is the coupling coefficient. Then the range of k is 0 less than or equal to k less than or equal to 1. Sir, why this k term is defining here? Because in the total pi 1 flux, the total pi 1 flux is not linked with the both the coils. Only portion of the flux is linked with the both the coils. Then how much portion? Let's assume that k times of pi 1 it is linked. But that k is never be greater than 1. It must be in between 0 to 1. Then this is the pi 2. Mutual flux. K times of total flux is linking with the both the coils. That is pi 2. Now, with this knowledge, now you can define what is the self-inductance. The self-inductance equal to, here self-inductance of which coil you can define, students? Coil 1 only, because coil 1 only carrying the current. Coil 1 only carrying the current. Then the self-inductance of coil 1. Coil 1. Then what is L1? Because which coil is carrying the current? Coil 1 is carrying the current. The self-inductance L1 equal to, yes friends, N1 into pi 1 by The current passing through this coil is I1. N1, just like this fundamental I given N pi by I formula. N pi by I formula. Like that, here the number of turns is N1. N1 into pi 1 by I1. We can also write like this in terms of the flux linkage. What the number of turns into flux is the flux linkage. Psi by I1. That we can write psi 1 by I1. What is psi 1 here? Where psi 1 equal to N1 into pi 1, that equal to flux linkage. Flux linkage. Then we can also define mutual inductance. We can define the mutual inductance. Then what are the mutual inductance, friends? Here I am defining M12. What is M12 here? Mutual inductance of coil 2 with respect to. Here we are defining the mutual inductance of coil 2 because which coil is carrying the current? Coil 1 is carrying the current. That's why there is a mutual induced EMF in coil 2. If coil 1 is carrying the current, students, if coil 1 is carrying the current, here there is a self-induced EMF. Here there is a self-induced EMF. Then coil 2, there is a mutual induced EMF. That means for which coil we want to define the mutual inductance? For coil 2, we want to define the mutual inductance. Okay. Then how to write the mutual? What is M12 here? Mutual inductance of coil 2. Mutual inductance of coil 2. Inductance of coil 2. Yes, friends. With respect to which coil? With respect to coil 1. We are defining with respect to coil 1 because coil 1 is carrying the current. Coil 1 is carrying the current. Then how to write mutual inductance of coil 2? Then M12 equal to, yes, N2 into how much flux is linking with coil 2? Total pi 1 flux linking or pi 1 is linking or pi 1 2 is linking? Come on. How much flux is linking with coil 2? Is pi 1 or pi 1 or pi 1 2, sir? It's a pi 1 2. How much flux is linking? Pi 1 2 is linking. But current is passing in which coil? This is mutual inductance. The current is passing in which coil? Coil 1. The current is passing in coil 1. We can also write like this psi 1 2 by, we can also write this is equal to psi 1 2 by I1. This is M12 equal to psi 1 2 by I1. Is it correct, friends? This is the mutual inductance of coil 2 with respect to coil 1. With respect to coil 1. Mutual inductance of coil 2 with respect to coil 2. What is psi 1 2? The psi 1 2 equal to N2 into pi 1 2. This is the flux linkage in coil 2 with respect to coil 1. Psi 1 2 is flux linkage in coil 2 with respect to coil 2. Sorry, with respect to coil 1. We can also write like this M12 equal to N2 into pi 1 2 by I1. Pi 1 2 by I1. That is N2 into, what is pi 1 2? What is pi 1 2, students? K into pi 1. What is pi 1 2? Pi 1 2 equal to K into pi 1. That I am writing K into pi 1 by I1. Okay, this is M12 in terms of mutual coupling. In terms of mutual coupling coefficient, with respect to coupling coefficient, this is the formula that you remember. This is the equation, relation 1. And you can also define self-inductance. The self-inductance equal, self-induced EMF equal to minus L1 into di1 by dt because current is passing in coil 1. We can also define the mutual induced EMF. What is the mutual induced EMF? The mutual induced EMF equal to minus M12 into di1 by dt. di1 by dt. Is it correct? Because here we are defining the mutual inductance is between 1 and 2. That is mutual inductance of coil 2 with respect to coil 1. This is about how to write the self-inductance formula and mutual inductance formula. Let's see the case 2. Let I2 is the current in coil 2 while coil 1 not carries any current. Now here I am assuming that exactly opposite, students. Let assume that coil 1 is not carrying the any current. That means I1 equal 0. But coil 2 is carrying the current. Coil 2 is carrying the current. Then pi 2 is the total flux from coil 2. Total flux from coil 2. Yes, friends. Pi 2 is the leakage flux of that links with only coil 2. Only coil 2. Pi 2 is the leakage flux that links with only coil 2. Pi 1 is the common flux or mutual flux links with both the coils. Links with both the coils. Now what the total flux in coil 2? The total flux of coil 2 is that leakage flux of coil 2 plus the flux which links with the both the coils. This is the total flux of the coil 2. Very important, students, please concentrate. Clear? Pi 2 equal to pi 2 plus pi 1. Here also same, let the number of turns in coil 1 is N1, number of turns in coil 2 is N2. Clear? Now tell me, what is the self-inductance of coil 2? What is the self-inductance of coil 2? L2 equal to, yes, N2 into pi 2 by I2. Is it correct, students? This is equal to psi 2 by, that equal to psi 2 by I2. Because here which coil is carrying the current? Coil 2 is carrying the current. That's why you are defining the self-inductance of the coil 2. Coil 2 is carrying the current. That's why you are defining the self-inductance of the coil 2. Next. Then what is pi 1 here? Pi 1 is not equal to pi 2. Only portion of flux only which links with the both the coils, that is k into pi 2. K into pi 1 equal to k into pi 2. Then what is the k here? Coupling coefficient whose value is 0 less than or equal to k less than or equal to 1, where k is the coupling coefficient. K is the coupling coefficient, where k is the coupling coefficient. Okay, students? Okay, this points you remember how to write the self-inductance if only coil 2 is carrying the current. Now here I want to write the mutual inductance also. Then what is the mutual inductance? Here we want to define M21. What is M21 stands for? Mutual inductance of coil 1 with respect to coil 2. Because which coil is carrying the current here? Coil 2 is carrying the current. Mutual inductance of, yes friends, mutual inductance of, yes, coil 1 with respect to coil 2. With respect to coil 2. Because coil 2 is carrying the current, that's why you are defining with respect to coil 2. Now you define what is M21. Mutual inductance of coil 2. Sorry, mutual inductance of coil 1 means you take the N1 number of turns. Then pi 1 by, which coil is carrying the current? Coil 2, that is by I2. This is also equal to psi 1 by I2. Psi 1 by I2. Okay, this is the mutual inductance of coil 1 with respect to coil 2. That is M21. You can also write M21 in terms of coupling coefficient. So that is N1 into, what is pi 1? Pi 1 equal to k into pi 2 by I2. K into pi 2 by I2. Okay, this is about what this one? This is the mutual inductance of coil 1 with respect to coil 2. Clear, friends? But here I am giving the note point. Please concentrate. If distance between the coils and permeability of medium is constant. See, for a given coupled coils, once we can design the coupled coils, the distance between the two coils is same, and whatever the medium we are using between the two coils, it remains constant. Once it remains constant, if the distance between two coils, if the distance between between two coils. If the distance between two coils and medium between two coils remains constant, then if you define the mutual inductance of coil 2 with respect to coil 1, or if you define the mutual inductance of coil 1 with respect to coil 2, both are equal, then that is equal to mutual inductance M. These two are equal because once we can design, the distance remains same and the medium between the two coils is also same. If the medium changes or distance between the two coils changes, then automatically the mutual inductance is also changes. Understand, students? Now with this knowledge, now we are defining the coefficient of coupling. Very important. We are defining the coefficient of coupling. What the coefficient of coupling, students? To get the relation between the self and mutual inductance, coefficient of coupling may be defined. The coefficient of coupling is defined in order to get the relation between the mutual inductance and the self-inductance. Then what is the definition of the coefficient of coupling? The degree to which the mutual inductance approaches its maximum value is given by the coefficient of coupling. The degree to which M approaches its maximum value is described by the coupling coefficient. That is, the coupling coefficient indicates how much closely coupled these two coils. Is it a weak coupling? Is it a strong coupling? It is a good coupling. That is given by the coupling coefficient. Or how much maximum mutual inductance we are achieved. That is also given by the coupling coefficient, students. That is to get, mainly the coupling coefficient is defined to get the relation between the self-inductance and the mutual inductance. Now, I want to find what is the expression for the mutual inductance and self-inductance. To get the expression for mutual inductance and self-inductance, then from that we can define the coupling coefficient. Let's consider yes, friends, the product of, let's consider the product of M12 and M21. M12 and M21. Then if you take the product of M12 and M21, friends, then what you can get? M12 into M21. What is M12? That is M12 equal to M21 equal to M. That is M into M. For same coupled coils, the medium is constant and the distance is also constant. That is equal to M square. This is equal to, what is M12, students? We know that M12 equal to N2 into pi 12 by I1. Is it correct? N2 into pi 12 by I1, or directly I am writing K into pi 1 by I1. N2 into, this is from equation 1, K into pi 1 by I1. This is into N1 into K into pi 2 by I2. Pi 2 by I2. Then from this one, what the M square equal to? M12 and M21 I already given the expression. That expressions I am writing here. Yes, friends, you simplify this one. Shall I write like this? You modify this one. N1 into pi 1 by I1 into N2 into pi 2 by I2 into K square. This is K into K, that we are getting the K square. What is N1 into pi 1 by I1? Then M square equal to, what is N1 into pi 1 by I1? L1. What is N2 into pi 2 by I2? L2 into K square. Yes, friends. Now from this, what is M equal to? M equal to K into square root of L1 into L2. Very, very important formula, 5-star formula. This is the relation between mutual inductance and self-inductance. That is related through coupling coefficient. that is related through coupling coefficient. Therefore, what is the coupling coefficient K, students? What is the coupling coefficient K? The coupling coefficient K equal to M by square root of L1 into L2. Very important relation for any competitive exams. The coupling coefficient K equal to M by square root of L1 into L2. Any doubts? Is it clear, students? Respond. Any doubts? Yes. Now, therefore, what is K here? K equal to M by square root of L1 into L2. That is a coefficient of coupling. What the range of K? The range of K is 0 to 1. That is, M is always less than or equal to L1 into L2. But point to remember, students, ideally, what is the value of K? Equal to 1. But practically, what is the coefficient of coupling? The coefficient of coupling is always less than 1. Practically, always K is less than 1, but ideally K equal to 1. K equal to 1, the coils are called perfectly coupled coils. Yes, friends. K less than or equal to 0.5, the coils are called loosely coupled coils. K is greater than or equal to 0.5, the coils are called tightly coupled coils. That means how much coupling is there, that is decided by the coupling coefficient. The larger value of coefficient of coupling are obtained with coils which are physically closer, which are wound or oriented to provide a larger common magnetic flux, or which are provided with a common path through a material which serves to concentrate and localize the magnetic flux, that is high permeability of the material. Then how to achieve the larger value of the coefficient of coupling, students? To achieve the larger value of the coefficient of couplings, the coils must be placed very closely, very close. Then we can get the more coupling coefficient. Or whatever the core we are using, that core must be high permeability. For example, with respect to transformer also, this is the core. On this core, we are placing the coils. These coils are magnetically coupled through core. Whatever the core we are using, that core must be high permeability to get the maximum coupling coefficient. High permeability. Once this core is having high permeability, then it offers the less reluctance. Once it offers the less reluctance, then maximum flux is linked with both the coils, then the coupling is also becomes high. That's why generally in a transformer, why you are preferring that the core is made with silicon steel. The core is made with silicon steel or CRGO steel core because it offers the high permeability or it offers the less reluctance. Then we can get the maximum coupling between the coil 1 and the coil 2. That's why one method is to achieve the maximum coupling, the distance between the two coils must be reduced. That electrical students, this concept also. You have the different types of winding procedure with respect to different types of placement of windings, different types of placements of winding in a transformer. Okay, in order to reduce the distance between the two coils, then how you are placing the windings, that why you are reducing the distance between the two coils? To improve the coupling. Okay, that points you remember, students. Okay, this is about what the concept of self-inductance and mutual inductance. Then what is the relation between the self-inductance and mutual inductance using the coupling coefficient or coefficient of coupling. Any doubts, friends? Come on, is it okay? Yes. The next very important topic, here I'm not giving the derivation for time being, but direct formulas is important based on this topic. Electrically coupled inductors in series. If the inductors are connected in series, but here there is a two types of connections, mutual aiding and mutual opposing. What do you mean by mutual aiding and what do you mean by mutual opposing? Yes, friends, first we will see the mutual aiding. It is a series connected coils, but it is a mutually aiding. The dots are issued at similar terminals, then it is nothing but a mutual aiding. Similar terminals means, for example, these two coils are mutually aiding. These two coils are mutually aiding. And this connection also same. This connection also same. This also mutually aiding connection. These two coils also mutually aiding. Either this connection or this connection, both are mutually aiding. Similar terminals. That means for this coil, let's assume that the dot is issued at starting terminal. For this coil also, the dot is issued at starting terminal. That is at similar terminals. For example, take these two coils. For this coil, the dot is issued at the ending terminal. For this coil, the dot is issued at ending terminal. That's why if the dots are issued at similar terminals, then it is nothing but a mutually aiding. Or you can also analyze with respect to current directions also. For example, I am taking this is the direction of the current. For this coil, current is enter at this dot, and is also current is entering at the dot. That's why it is a mutually. And you take the current direction. For this coil, current is leaving at this dot. For this coil, current is leaving at this dot. That's why if the current is enter at both the dots, or if the current is leaves at both the dots, then also it is a which one? Aiding connection. Clear, friends? Generally, you can analyze based on the dots are issued at which terminals? Is it similar terminals or dissimilar terminals? Generally, dots are issued by the manufacturer. Dots are issued according to sense of winding. Dots are issued at sense of winding. From where the winding is started or where the winding is terminated. If the dots are issued according to starting winding, or dots are issued according to termination of the windings. Understand? Okay, that point to remember. Then, in the case of mutually aiding means the flux due to both the coils is aiding. That is the meaning. Mutually opposing means the flux due to both the coils is opposing. Okay, that is nothing but a mutually opposing, students. Clear? Okay, this is mutually aiding connection because the dots are issued at similar terminals. Now, in this case, what is the equivalent inductance? Let this is the L1 and this is the L2. The mutual inductance between the two coils is M. Because these two coils are mutually coupled also, let this mutual inductance is M. These two connections are same, sir. It is also mutually aiding, it is also mutually aiding. Then in this case, what is the L equivalent? I'm not giving derivation, not required. Yes, friends, what is the L equivalent? Then in this case, L equivalent equal to, very important formula, L1 plus L2 plus 2M. L1 plus L2 plus 2M. If the two coils are series connection and mutually aiding, then what is the L equivalent? L1 plus L2 plus 2M. This also mutual aiding connection, this also mutual aiding connection. This is L1 and this is L2. It's very simple, sir. Sir, how I am getting this formula, sir? How I am getting this formula? Say, for example, just understanding purpose I am giving. This is V. In series connection, current remains constant. Current remains constant. Let this is the voltage across this coil is V1. Voltage across this coil is V2. Then what is V equal to, students? V equal to V1 plus V2. V1 plus V2. Yes. What is V1? You can write this V1 equal to L1 into di by dt plus L1 into di by dt. Here I am writing the, what is the V1? V1 is nothing but a, how we can write V1, students? This is L1 into di by dt, but these are aiding connection. These are aiding connection means plus M into di by dt. Same current only. Then V2, how we can write? L2 into di by dt plus M into, and between this coil and this coil also M. That is M into di by dt. Okay. Then in solving of the problems in detail, how to write these equations also I will explain. Then take the di by dt is common, L1 plus L2 plus 2M into di by dt. Then what is V equal to? L equivalent into di by dt. Then what is L equivalent here? The L equivalent equal to L1 plus L2 plus 2M. By derivation only, but not required, but very important formula for any competitive point. That is L equivalent equal to L1 plus L2 plus 2M. Clear, friends? What is the mutual aiding? If the dots are issued at similar terminals. Next, inductors in series but mutually opposing. Mutually opposing. What do you mean by mutually opposing? The dots are issued at dissimilar terminals. See this one, friends. For this coil, dot is issued at starting terminal, but this is for ending terminal. For this coil, the dot is issued at ending terminal. For this coil, this is the ending. For this coil, this is the starting. That's why it is a similar terminals or dissimilar terminal, students. Come on. Similar or dissimilar? It is a dissimilar terminals. Even you can analyze according to current direction also. In two coils, if the current is enter at one dot, if the current is leaving at another dot, then it is a mutually opposing. Mutually opposing. Let the mutual inductance between these two coils is M. Even the mutual inductance between these two. These two connections are same. This also mutual opposing. This also mutual opposing. Mutually opposing. Then what is the L equivalent, students? The L equivalent equal to L1 plus L2. It's a minus 2M. L1 plus L2. It's a minus 2M. Clear, friends? Okay, this is about L equivalent. L1 plus L2. It's a minus 2M. These inductors are connected in series, but it is mutually opposing. Next, inductors are in parallel, but it is a mutually aiding connection. Mutually aiding means that point already you know. The dots are issued at similar terminals. For this coil, the dot is issued at starting terminal. Yes, it is also at a starting terminal. That this is the L1, this is L1, L2. For this coil, dot is issued at ending terminal. And it is issued at ending. That's why this also mutually aiding. Yes, friends. That this is in parallel connection, current is divided. This is I1 and this is I2. You can write the current formula here. But in series connection, you write the voltage formula. But here current is divided. This is I1 and this is I2 and this is I. Not required any derivation during solving of the problems. If any equations are came, then how to write that I will explain. Yes, friends. Then now you tell me what is the L equivalent here. Very important. Come on, write down. What is the L equivalent? Two coils are connected in parallel, but it is an aiding connection. Two coils are connected in parallel, but it is an aiding connection. Yes, friends. How we can write? This is equal to L1 L2 minus M square by L1 plus L2. It's not plus 2M. Here we can get minus 2M in parallel connection. Even though it is aiding connection, here we can get the, which one, friends? Minus 2M. Don't confuse. By derivation only we can get this one. This is the L equivalent. That is L1 L2 minus M square by L1 plus L2 minus 2M. Next. Inductors are in parallel. The dots are issued at dissimilar terminals. It's aiding connection or opposing connection, students? Come on. Aiding connection or opposing connection? Yeah, this is I1, this is I2, and this is I. Yes, this is I1, and this is I2, and this is I. Aiding connection or opposing connection? It is opposing connection. Then what is the L equivalent, students? L equivalent equal to L1, L2 minus M square by, yes, friends, L1 plus L2. Here you can get plus 2M. In opposing connection, in denominator, we can get the plus 2M. Okay, this is about inductors in series and in parallel. In series connection, again two connection, aiding connection and opposing connection. In parallel connection, again two connections, aiding connection and opposing connection. Clear? The next one more topic. This is also very important. Yes, friends. Let these two coils are mutually aiding. Then what is the T equivalent of this circuit? These two coils are mutually opposing. What is the T equivalent of this circuit? Not required any derivation. Yes. Concentrate, friends. Let this is LA and this is the LB and this is the LC. We are writing as a T equivalent of this one. This is LA and this is LB and this is LC. Then what is LA equal to? Where LA equal to L1 minus, let the self inductance of this coil 1 is L1. This is coil 2 is L2. The mutual inductance is M. Yes. Then what is LA equal to? LA equal to L1 minus M. What is LB equal to? L1 minus M. Then what is LC equal to is M. And this is aiding or opposing, mutually opposing, because the dots are issued at dissimilar terminals. Then in this case, just replace M by minus M. In mutually opposing, replace M by minus M. Replace M by minus M. Then if you replace M by minus M, what is LA? L1 minus of minus plus. L1 plus M. What is LP? Is equal to L2 plus M. It's L2, sir, not L1. It is L2 plus M. What is LC? LC equal to minus M. Okay, this is the T equivalent for mutually opposing. This is the T equivalent for mutually aiding. Clear, friends? Then if any coupled circuits are given, if it is converted into T equivalent, mutually coupling, if it is converted into mutually coupling, that mutually coupling is converted into T equivalent in aiding connection and opposing connection. Now this also mutually aiding or opposing. Can anybody answer? Is it a mutually aiding or opposing, students? This is mutually aiding or opposing. Mutually, come on, it's a mutually aiding. Two coils are mutually aiding because dots are issued at similar terminals. Now it is a pi equivalent circuit. It is which one? Pi equivalent circuit. Now it is converted into pi equivalent circuit. Let this is the LA and this is the LB and this is the LC. The notation is given capital letters. No, not the problem. This is LA and this is LB and this is LC, whose formulas are given like this. Okay, this is not required any derivations. Very important. It's a pi equivalent. Direct formula based questions we are expect in GATE exam. LA, LB and LC, students. What is LA and what is LB and what is LC? For mutually opposing, what you can do? For mutually opposing, in above formulae, replace, what you can do, students? In above formulae, replace M by minus M. M by minus M. Replace M by minus M if it is asked for mutually opposing case. But this I am giving for mutually aiding case. What is LA, what is LB and what is LC? Okay, this is about what exactly series aiding and series opposing, parallel aiding, parallel opposing, then how to convert coupled circuit into T equivalent, how to convert coupled circuit into pi equivalent. Clear, friends? All are understood? Okay. Here I am giving one example. You please try to answer this question. That this is 4 millihenry and this is 5 millihenry and this is 6 millihenry. This is 4 millihenry, this is 5 millihenry and it is 6 millihenry. The dot is issued at this point. Here also dot and this is the dot. Between these two, this is 2 millihenry. Between these two, this is 3 millihenry. 3 millihenry. Then what is the equivalent inductance? Any answer? Option A. 13 millihenry. Option B, 11 millihenry. Option C, 10 millihenry. Option D, 6 millihenry. Any answer? Yes, friends. Can anybody respond? Chat your answer. Message your answer in a chat box. Yes. Why nobody is responding? Yes. It's very simple. You are finding the L equivalent. Yes, friends. What is the solution for this problem? The L equivalent equal to, listen, all the self-inductance. First add all the self-inductance. 4 plus 5 plus 6. Now analyze the mutual inductance. Yes. See, this is the mutual inductance with respect to these two coils. For this coil, it is a starting terminal. For this coil also, it is a starting terminal. Clear or not? For this coil, this is the starting terminal. A dot is issued at starting terminal. For this coil also, dot is issued at starting terminal. Clear or not? That's why this is the dot is issued at starting terminal. That's why plus mutually aiding. 2 into 2. 2m na? Plus 2m. Next. Next, analyze wherever the mutual inductance is defined, all those two coils, you can analyze that. See, this is here also mutual inductance is defined. For this coil, dot is issued at starting terminal. For this coil, dot is issued at ending terminal. Clear? That's why it is a mutual aiding or opposing. Opposing. Opposing means minus. Minus 2 into how much mutual inductance is given? 3. And how much you can get, students? 4 plus 5, 9, 9 plus 6, 15. 15 plus 4, 19, 19 minus 6. How much you can get? 13 millihenry. Clear or not? Any doubt? So, okay. Like this, we can write down the different models of problems. Students, today I'm taking only 1 hour only. Okay. I'm ending the session. Then tomorrow, maximum I will finish the tomorrow. I will finish this coupled circuits. Then after that, I will start the two-port networks. Then tomorrow class, I will finish this. Then I will start the uh, two-port networks and transients. Next two topics are there: two-port networks and transients. With that, network theory will complete. Okay, friends, I'm ending the session. Thank you. Is it okay? Okay, thank you.
బ్రష్ వేసుకుంటారమ్మా